we have seen modeling of step voltage regulator in the last 2-3 lectures, and today's lecture we will see load models in the distribution system. So, before going to the load model, let us see what we have studied in the step voltage regulator modeling section of this particular chapter. So, we have seen why voltage regulation is required, that is basically what are the effects of under voltage or over voltage on distribution system components. And then we have seen various techniques which you can use to control the voltages over the distribution feeder, and those are basically we have seen OLTC, voltage boosters, step voltage regulator, capacitor banks. Then we have seen different types of regulator, those are type A and type B regulator, both are almost same, only mirror image of each other. So, basically type B regulators are widely used. So, we have studied the type B regulator in detail, and we have got the voltage and current relationship on primary and secondary side of the voltage regulator. Then we have seen the function of what is called as a line drop compensator circuit, and we have seen that it is basically required to control the taps of your regulator based on voltage at the far end of your feeder. And then we have seen modeling of 3-phase regulators. First we have seen Y connected, then closed delta connected, then open delta connected 3-phase regulators. And to understand it better, we have seen few examples, one example on single phased regulator, another example on 3-phase open delta kind of regulator. Now, let us start what is called as load models. Before going to the load models, first we will see why load models are required. So, if you know while doing the load flow studies in your BTech class or undergraduate course of power system analysis, you might have used constant real and reactive power loads. Means in each iteration of your load flow studies, your power remains constant. Means this first load which I have shown it here, that is nothing but your constant real and reactive power, that is called as constant PQ kind of load. And in this particular load, your P and Q values of the load remain constant throughout all iteration. We are not going to change. So, you might be remembering you are not changed values of P and Q during the iteration. Even the voltage changes, P and Q will remain constant. Basically this happens in case of induction motor. So, approximately it will not be exactly constant one, but approximately induction motor load or air conditioning kind of load you can model using constant real and reactive power model. So, in this case we can see that if there is say a induction motor kind of load and which is connected at the end, and then if you see the voltage at this end, if this voltage increases, what will happen? This load will try to keep Vi constant. So, when voltage is increasing, your current through the network will go down to keep the power of this load constant, PQ of this load constant. Similarly, when voltage decreases, it will try to take more current from the system. So, when the voltage decreases for this particular kind of load, what will happen is more current will flow through the network and it will create more I square R losses. And also inside the motor there will be higher I square R losses. So, this is how your constant PQ load will behave. Another type of load is called as constant impedance load. Here the impedance of the load remains constant. The examples of this load are incandescent lighting, resistive water heating, cooking loads which are basically based on your resistive heating coils. Those kinds of load which are basically based on resistive heating kind of coils, those can be modeled as a constant impedance loads. Now, if you see the behavior of this load, it will be exactly opposite to your constant PQ type of load. So, this is your constant impedance kind of load. So, this impedance of this device is say constant. So, in this case your voltage, so impedance is remaining constant, then your current will be just voltage divided by your impedance which is constant. So, when your voltage goes up, your current also goes up into this model, and when voltage goes down, current also goes down, which is exactly opposite of your constant PQ kind of load. So, in this case, when you are decreasing the voltage, you can see that current is decreasing. So, whenever we keep lower voltage here, your current is decreasing and you are getting lesser I square R loss into your distribution network, or if this is feeder here. So, feeder less amount of current is flowing, that is why less I square R loss. So, this particular characteristics of this load is used in what is called as CVR. So, it is called as conservation voltage reduction, and in conservation voltage reduction, if your distribution system has majority of constant impedance kind of load, then what they do, they will try to put the low voltage across the feeder as low as possible. However, we have to keep limit into the mind. We know that there is only plus minus 10% variation is allowed. So, we can operate this point at say 0.9 nominal voltage, and in that case, if the plus minus 10% is allowed, in that case your current will be also decreased by 0.9 and then your I square losses into the system will become you can say 0.8 per unit, because it will be actually I square R. So, I is 0.9 multiplied by 0.9, so it will become 0.81. So, your losses will decrease 20%. So, if you are decreasing voltage by 10%, your current is also decreased by 10%, and in that case your losses into the system will decrease by 20%, around 20%. So, this philosophy will be used in what is called as conservation voltage reduction, where the majority of the load in your distribution, if they are constant impedance load. Then third type of load is called as constant current load, and constant current load, whatever voltage across your device, if this is your load, whatever voltage across this device, your current will remain constant, current is not going to change. So, even your voltage at this load increased or voltage at this load decreased, your current is remaining constant. So, losses will not change in this type of load. The examples of this kind of load are welding, smelting or electroplating operations. Basically, they require constant current. So, even though voltages are low or high at that particular end, your current is remaining constant. However, when we are considering load for say load flow analysis or any type of analysis, what we do, we take combination of load, means we do not model exactly the each device or particular device. Instead of that, we actually collectively of many devices we take together or many houses we take together, and we model it as a lump load at that particular point. So, load will be always kind of mixed type, means there will be some equipments which are having constant PQ kind of characteristic, some equipment will be having constant impedance kind of characteristics, and some equipment will be having constant current type of characteristics. So, if you are modeling all the three types of load together, you are having two models available. One is called as polynomial model, we will see that, and then another is exponential model, which consists of all the three types of load. Let us see one by one. We will start with constant real and reactive power load. So, since we are considering distribution system, we should always talk about three-phase system. So, let us consider your three-phase load. So, you are having those load here. So, one phase, this is another phase, and this is three loads which are connected in say star, delta also we will consider afterwards, and this is say A terminal, this is your C terminal, this is your B terminal, this is your current IA, IC, or I will say since it is load current, so ILA, ILC and ILB. Now, this load is having say power SA, complex power, voltage across this load is say VAN, this is SB, voltage across this is SBN, this load is say SC, and voltage across this is say VCN. Now, this since it is complex load, SA will be equal to SA and it will be having some angle say theta A. Then your SB will be equal to magnitude will be SB and say angle of it is theta B. They may be actually unbalanced loads. So, all the thetas as well as magnitudes may different. Then SC will be equal to SC magnitude and angle will be theta C. And then voltages VAN will be having magnitude of VAN and angle say delta A. Voltage BN will be VBN and its angle will be delta B, and VCN, its magnitude is VCN and angle say delta C. If these are balanced voltages, the magnitudes of 3 voltages will be same and this delta A will be equal to 0. This delta will be say minus 120 degree shifted 120 degree and then it will be plus 120 degree shifted. However, as I told you, all these loads as well as voltages may become unbalanced in case of distribution system. In that case, these delta A, delta B, delta C, they may not be 120 degree phase shifted as well as your magnitudes also will not be same. So, you have to give that is why we have to represent it by different angles here as well as magnitudes may be different. So, in that case we can easily calculate. So, in this case many loads flow studies, the loads will be modeled as equivalent current injection, even generators will be modeled as equivalent current injection. So, whatever shunt components like capacitor, loads and generators, they may be modeled as equivalent current injection. So, basically we need to calculate how much current is getting injected into the system. So, in that case ILA can be easily calculated from this data. So, it will be SA divided by VAN and SA is actually SA angle theta A, VAN is angle having angle delta A and you have to take star of it. So, in this case your VAL will be magnitude of SA divided by magnitude of VAN and this angle will be delta A minus theta A, which is basically I can say IAL A magnitude and its angle which is basically this angle, I can say just alpha A. Similarly, I can get IL B current which will be equal to SB magnitude of this divided by VBN magnitude and its angle will be delta B minus theta B, and IL C load will be equal to SC magnitude divided by VCN magnitude and its angle will be delta C minus theta C. So, these are nothing but equivalent current which are coming out or current injected will be opposite of that. So, basically we have got the current which are flowing to the load which we can be calculated like this. Now, let us consider delta connected load. So, in case of delta connected load it will be modeled like this. So, these are 3 delta connected loads. So, this we can connect to terminal A, this we can connect to terminal B and this we can connect to terminal C. So, this is your ILA, this will be ILB and this will be ILC. Now, this current is ILAB, this current will be ILBC and this current will be ILCA which will be flowing basically like this. So, ILBC will be like this. So, in this case similar to our star connection we can again write the equation. So, in this case SAB which is basically load between A and B phases will be having SAB magnitude and its angle is say theta AB. Similarly, SBC will be SBC and its angle will be theta BC and SCA will be having SCA magnitude and its angle will be theta CA. and voltages will be VAB will be VAB magnitude and its angle will be delta AB, VBC will be having VBC magnitude and its angle will be delta BC, and VCA will be having VCA magnitude and its angle will be delta CA. And in this case also we can easily write equation similar to what we have seen earlier. Your current ILAB will be just depend upon SAB divided by its AB angle theta AB divided by VAB angle, these are magnitudes, angle delta AB, and you have to take complex conjugate of it, which will be equal to SAB magnitude divided by VAB magnitude, and its angle will be delta AB minus theta AB. Similarly, I can write for other two currents, ILBC will be equal to SBC magnitude divided by VBC magnitude, and its angle will be delta BC minus theta BC, and ILCA will be equal to SCA magnitude divided by VCA magnitude, and its angle will be delta CA minus theta CA. Now you got your delta currents. However, we have seen that for all this study we need line currents so that they can be injected during the power flow. So we are not keeping anything which is basically delta connected while doing load flow studies or short circuit connect. So you have to get the equivalent line current. So we have seen that how to convert your delta phase current to the line currents. So we know that the conversion matrix is basically your K matrix which you have seen. So that K matrix is generally your ILA, ILB and ILC, which are basically line currents, which will be equal to, you have seen that it is 1 0 minus 1 minus 1 1 0 0 minus 1 1 into your delta currents ILAB, ILBC and your ILCA. So basically this is nothing but your ILABC matrix, which is K matrix which you have seen earlier, and it is IDL ABC. So we have seen how to get the injected current in case of star connected load and delta connected load. So every time I will not go for delta connected load, you can easily derive them if you know how to do it in star connection. So for other loads I will just go for only star connection. Now let us consider your constant impedance kind of load. So we have seen the behavior of constant impedance kind of load where the impedance of the load is remaining constant. So what you have to do is, first you have to get the value of impedance, and then whenever your voltage across that impedance is changing, injected current is calculated based on that constant impedance. So let us see how we can do it. So in this case again I will be taking your SA, which will be equal to SA magnitude and its angle will be theta A. SB will be equal to SB magnitude and angle will be theta B, and SC will be equal to SC magnitude and angle will be theta C. And voltages we already seen, they are VAN and its angle is delta A, VBN and its angle is delta B, and VCN is actually equal to VCN magnitude and its angle is delta C. Now these are say actual voltages here. However, there will be always the voltages, you can say nominal voltages will be defined for this particular load. So say nominal voltages, so I am saying nominal or rated voltages, magnitude for this particular load is say VAN0, which is I am saying nominal voltage of this particular load. Nominal voltage for this load is say VBN0, and this say VCN 0. So these are basically nominal voltage, rated voltages. So these are rated loads and these are rated voltages. So from these rated quantities, first get impedances of the loads. So impedance of the load, first load, say this load will be calculated, say this is impedance is ZA, this impedance is ZB and this impedance is ZC, and as I told you, throughout the calculation impedance will remain constant here because these are constant impedance kind of load. So ZA will be calculated like this, it will be VAN 0 square divided by your SA star, or you can say, so this will basically equal to VAN 0 square divided by SA angle minus theta A, because we are taking complex conjugate of it and its magnitude here. So this will be equal to VAN 0 its square divided by SA, which will be magnitude of this impedance, and impedance angle will be theta A. Okay. Similarly, ZB will be VBN 0 divided by SB, magnitude of this square, and angle of it will be theta B. Similarly, ZC will be equal to VCN 0 its square divided by your SC, and its angle will be theta C. And as I told you, throughout the operation these impedances will remain constant, and these impedances we have got from the nameplate ratings of the load. So nameplate rating gives you the load values as well as your rated voltages. Rated voltage magnitude will only we need here. So using the magnitude we have calculated impedances. Now when we want to calculate injected current for different voltage level which are different than your nominal voltages, then those can be calculated. So your ILA will be equal to VAN, it must be different voltage than your, it may be, I am saying it will be different voltage than your nominal voltage, and angle is delta angle may also different, and then divided by your ZA magnitude angle theta A. This is your magnitude. So in this case I can easily get it will be VAN magnitude divided by ZA magnitude, and its angle will be delta A minus theta A. Similarly, I can write for ILB, which will be equal to VBN divided by your ZB, angle will be delta B minus your theta B, and your ILC in this case will be VCN magnitude divided by ZC magnitude, and its angle will be delta C minus theta C. The procedure in this case, as I told you, from the nameplate rating, first you have to get the impedances of the load, and once you get the impedances you have to use these impedances to get the injected current in the network, that is voltage divided by impedances will give you injected currents. So we are not going for delta connection because it will be easier, like we have already seen it for constant PQ kind of load. Now let us say how constant current loads behave. So in this case you have to first calculate the values of constant currents. Now again I am taking this SA, which will be equal to SA magnitude and angle theta A, SB will be SB magnitude angle theta B, and SC will be equal to SC magnitude angle theta C. And as I told you, nominal voltage I will first write. So VAN 0, which is nominal voltage or rated voltage of the loads, of the second load VBN 0, and third load VCN 0. Only magnitudes we need it here. Now in constant current load, current magnitude only remains constant, angle may change. So in that case current magnitude can be easily calculated. So current magnitude of load LA, so ILA magnitude can be calculated from SA magnitude divided by VAN 0 and its magnitude only given. Similarly, magnitude of B will be calculated SB magnitude divided by your VBN 0 magnitude, and then ILC will be equal to SC divided by SC magnitude divided by VCN 0 magnitude. So, this will give you the currents which are basically remain constant throughout the operation or throughout the load flow solutions. So, in that case, if there are different voltages than these nominal voltages, sometimes as I told you there will be different voltages. So, say the voltages now are say VAN angle delta A, VBN angle delta B and VCN angle delta C. Now, for these voltages, even though voltage will change, you need to keep the current magnitude constant. So, current injected current in this case there will be ILA will be equal to ILA magnitude always remain constant even the voltages change. However, the angle in this case will be calculated delta A minus theta A of the load. Similarly, ILB will be equal to ILB magnitude will remain same, and then it will be delta B minus your theta B, and ILC will be equal to ILC magnitude and delta C minus your theta C. And as I told you, many times your loads are mixed type of load. So, many times you need to consider all the three types of loads together, and in that case we have seen there are two types of model we use. One is called as polynomial load model, and in case of polynomial load model we represent load like this. So, P, which is actually basically voltage dependent. So, I can say VA, which is basically actual voltage, which will be equal to some A0, or we can say A0 plus some A1 into V actual divided by V nominal plus A2 into V actual divided by V nominal and its square multiplied by nominal power of the load. Okay, so, here P0 is nominal power of the load and V0 is nominal voltage of the load and VA is actual voltage at which we want to calculate the load. So, it is actual voltage during the load flow calculation. As I told you, voltages may change. So, at each iteration VA will go on changing. However, this V0 which is nominal and P0 which is nominal, it will remain constant. So, in this case if you see you are already considering all the three types of load. So, this A0 multiplied by P0 will represent basically constant power load, P0 multiplied by A1 multiplied by this VA divided by V0 will basically represent constant current load, and this P0 multiplied by A2 and multiplied by VA divided by V0 and its whole square will represent your constant impedance kind of loads. So, therefore, since they are mixed type of load, and in that case your A0 plus A1 plus A2 should be equal to 1. It should represent total 1 per unit load, and this is basically represent your percentage of three different kinds of loads. Exactly similar way I can write Q, which also depends upon your VA, and in this case your constants may be different, B1 plus B2 VA divided by V0 plus in this case okay B0 I will say this is B1 and this is B2 again it is VA divided by V0 whole square into Q0. Again Q0 is nominal reactive power of the load. So, in this case also total proportion of all the different types of loads will be equal to 1. So, in this case these coefficients are different because we know that real power and reactive power, they will behave differently with respect to voltage change. So, in this case if you observe your when your A1 or you can say A0 equal to B0 equal to say 1 and all other quantities are 0, that is A1 is equal to B1 is equal to A2 is equal to B2 is equal to 0. In that case I can write BVA is actually equal to your A0 is 1. So, the 1 multiplied by P0 will be actually just P0 here. Similarly, Q multiplied by Q, which is function of VA, will be equal to Q0. So, you can see that they are these loads now when A0 and B0 if they are 1, it is behaving as a constant power loads. So, this is nothing but constant power loads. And then when your A1 is equal to B1 is equal to 1 and all other quantities, that is A0 is equal to B0 is equal to A2 is equal to B2 is equal to 0. In that case we are getting P, which is VA, which will be equal to VA divided by V0 magnitude multiplied by your P0 and Q VA, which will be equal to VA divided by V0 into your Q0. So, in this case, since the power are proportional to your voltage change, this load is nothing but your constant current loads. And in third case, when your A2 is equal to B2 is equal to 1 and A0 is equal to B0 is equal to A1 is equal to B1, if they are 0, then your PVA is becoming equal to VA divided by V0 its square into P0 and Q, which is function of VA, its square into Q0. So, you can see that the powers are becoming proportional to your voltage square, and that is nothing but characteristic of your constant current constant impedance load. So, this is nothing but your constant impedance kind of load. So, depending upon your coefficients, the proportion of different types of load will change, and depending upon proportion of loads in your that particular node, we can calculate the current injected. Now, another type of load model which is again famous, which is called as exponential type of load model. So, in this case we represent load like this. So, your P, which is function of VA, again this V is actual voltage, which will be equal to P0 multiplied by V raised to some constant, or you can say VA divided by your V0 raised to some constant K1, and your Q, which is again function of VA, will be represented by Q0 multiplied by your VA divided by V0 and its some constant, another constant K2, as since K1 K2 will not be same, because as I told you, your behavior of Q and P will not be same with respect to your voltage, means change in P and change in Q will be very different when the voltage is changing. So, K1 and K2 coefficient, similar to earlier cases, again depending upon K1 and K2 values, your proportion of P and Q will change. So, general values of K1 and K2, they are generally between say 0.6 to 1.8 for general kinds of load, and then K2 is generally between 1.6 to 6. And depending upon your load pattern, it can also be estimated based on your if you know the variation of powers with respect to variation of voltage, if those curves are available, by curve fitting technique you can get this coefficient K1 and K2. Now, this for constant power loads, this K1 and K coefficient will be equal to 0. So, when this K1 and K2 they will be equal to 0, this load will behave as constant power, because in this case PVA will be equal to just P0 and QVA will be just equal to your Q0. Similarly, when K1 is equal to K2 is equal to 1, these loads will be proportional to your voltage ratio. In that case, in case of constant current, so this will happen in case of constant current loads, then K1, K2 will be equal to 1. So, in that case PVA will be equal to P0 multiplied by your VA divided by V0 raised to 1, and QVA will be equal to Q0 into VA divided by V0, and in this case we can see that these loads are proportional to voltage, that is why they are constant current load, and in case of constant impedance load, your K1 is equal to K2 will become equal to 2. So, in this case your PVA will be equal to P0 into V actual divided by V nominal square, and QVA will be equal to Q0 into V actual divided by V nominal its square. So, this is characteristic loads are proportional to your voltage squares. So, that is why it is characteristic of your constant impedance load. And let us see the effect of these load models on current as well as your power. So, in case of current, we have seen that in case of constant MVA load, whenever your voltage is increasing, to keep the power constant, your current has to decrease. So, whenever voltage is increasing, current will decrease in case of constant power or constant MVA load. In constant current load, by characteristic current will remain constant, and in case of impedance load current will be calculated, we have seen just V divided by Z, and Z is constant. So, when V is decreasing, your I also will decrease. So, when V is decreasing, your I also will decrease, or when V is increasing, your I also will increase. Then power relations, if you see, so here I am plotting power relation. So, when the percent voltage is changing, since in case of constant power load, your load should remain constant. So, that is why for constant power load is remaining constant. However, in case of constant current load, as the voltage increases and current is remaining constant, so current multiplied by current is increasing and voltage remaining current is remaining constant and voltage is increasing, means power has to increase. So, the change in constant current load will be something like this: as we increase the voltage, since the current is constant, your power will increase. In case of constant impedance load, we have seen that it is proportional to voltage square. So, this in that case, whenever your voltage is changing, your power will change with respect to voltage. So, you need to model the load accurately by taking different types of models. So, we have seen various types of model into this particular class, that is, those are constant impedance, constant current separately we have seen, and then we have seen two different mixed type of load models. Those are polynomial model, which is again called as ZIP model, because ZIP, which is basically represent constant impedance, constant current and constant power, and it is representing as polynomial of those three combinations. And then we have seen exponential load model. So, next time we will see accurate modeling of induction motor. Thank you.